So I would like to invite Dr. Jaichander Swaminathan to share his screen. And Dr. Jaichander is an assistant professor in the Department of Mechanical Engineering. He is my former colleague at IIT Gandhinagar. He also holds a chair position in, with regard to mainly for his work in the area of water. And his primary focus is on energy efficiency of desalination technologies. And today, I think he's talking about cheap and cost-effective desalination technologies. Over to you, Jay. You are muted.
Thank you. Yeah. Thank you so much, Babji, for the introduction and for inviting me to speak at this session. It's been a good experience listening to all the speakers before me, and I hope to build on some of the topics that have been covered previously. So let me just do slideshow mode. So as Babji mentioned, my work is primarily focused on energy efficiency of desalination. But recently, we've tried to focus a little more on the applied side, looking at industrial effluent recycling as an application of some of our work. And so that's essentially what I plan to share in today's presentation, with a focus on the textile dyeing industry. Okay, so in the industrial context, we often see that the effluent management is considered from the perspective of compliance, whereas we've discussed that it may make more sense to present a picture to them where it is seen as a resource rather than something that is enforced upon them from a government diktat. I think the outputs will certainly be better, but because currently it's more about managing the regulatory aspects, the effluent management and the effluent treatment is usually an afterthought, and it is contracted out for design from outside suppliers. So I feel there is a scope for a big picture or overall optimization of this area. Right. But of course, at the same time, the industries are really interested in managing the effluent treatment plant because it affects their operations significantly, and it's also a significant expenditure on their account and affects their bottom line nowadays. So my focus is going to be on the tertiary treatment step towards reuse. As I mentioned, because my work has focused on desalination, I wouldn't really be covering in much detail the primary and secondary treatment technologies. The way I think about it is that the water that comes out after the secondary treatment, the dissolved impurities are more or less going to remain unchanged. So that's why I'm highlighting here that the total dissolved solids remains unchanged. And that is where the desalination technologies come in as a tertiary treatment technology to enable recovery of not just pure water for recycling, but also potentially other resources for recycling in the industry. The extent to which resource recovery and recycling is going to be implemented in industry is going to be affected by several factors. First of all, as I mentioned, regulations play a key role. So we'll look at zero liquid discharge in particular, which is being mandated on several industries. The economics then also come into the picture, because once the regulations are there, how cheaply they can do it is also an important objective. And I think there are also market driving forces towards water recycling and reuse. From the perspective of sustainability, from a brand building perspective, it is also useful for these industries to be more careful in their resource usage, right? And some of the challenges are, of course, related to the nexus with energy and for the industry to remain price competitive with their competitors. One challenge that I particularly see is that compared to, say, for example, seawater desalination for drinking water production, which is a standard process which can more or less be implemented across the globe, in the industrial setting, it becomes very unique to each industry. So some of the proposals and methods that we come up with, it's slightly difficult to scale it up beyond the specific industry with which we work on. So broadly speaking, if we think about brine concentration towards zero liquid discharge, I'm highlighting here the conventional treatment steps as they exist today. So if the incoming water is salty, so let's say it's coming in at around 7,000 ppm TDS, first and foremost, we would always want to use reverse osmosis because this is the most established, well-developed technology, and it's also the cheapest among the technology alternatives as on date. And so we would like to push for as much recovery of water as possible with this reverse osmosis step. However, we are quite limited with the reverse osmosis because beyond a certain concentration, so once we have started separating out pure water from the solution, we get a concentrated brine. Beyond a certain concentration, the pressure required becomes too high to sustain the process with reverse osmosis. So often seawater desalination goes up to around 65,000, 70,000 ppm. But in the industrial setting, due to the more fouling nature of the water stream, the concentration is even more limited. Right? So what we usually do after the reverse osmosis step is to use thermal distillation technologies such as multi-effect distillation or multi-effect evaporators, sometimes multi-stage flash distillation, as well as mechanical vapor compression for further concentration of this water, this time to beyond saturation concentrations. Right? So this solution that comes out is basically like super saturated solution of the salts. And that can then be taken to a crystallizer or a solar evaporator, either to produce a solid waste or to recover specific salts for recycling. If you look at the energy consumption, you can see that the reverse osmosis step, even though it covers 85% of the incoming water, consumes only around 1.6 kilowatt hours of electricity per meter cube. Whereas the multi-effect distillation, which is only recovering 10% of the incoming water, but of course handling more salty waters, consumes around 0.3 kilowatt hours of electricity per meter cube of incoming effluent, but also 30 kilowatt hours of thermal energy per meter cube. So as a result, the operating expenditure associated with the multi-effect evaporator is much more significant compared to the RO, which is why I was mentioning that as a standard practice, it is preferable to push to as high a recovery as possible with the membrane-based desalination technology. So my focus will be on textile dyeing effluent reuse. This is work done in collaboration with SP Textile Processes Private Limited, located in Chittoor in Erode, Tamil Nadu. A couple of studies. One is focused on an integrated system level optimization, where we have tried to modify the solution chemistry to reduce the energy consumption in the effluent treatment. So this, I think, ties in with the professor's presentation in the beginning of today's session, where in addition to water, food, and energy, it was proposed that chemicals should also be a part of the nexus picture. So perhaps this is one avenue of exploration along those lines. And the other is related to treatment that is very specifically tuned to the industry requirements. So we'll start with our discussion on the first topic, which is how can we optimize the system as a whole. So if you look at textile dyeing, we need to understand the process before we think about how to modify it to enable cheaper effluent recycling. So in the process basically involves taking the fabric and exposing it to multiple baths. Right? Each bath is basically a water solution at a particular temperature. The fabric is immersed in this water solution for a certain amount of time, and some chemicals are added to impart specific properties to the fabric. So we can broadly classify these into three sets, where there are the preparatory bath steps and followed by the dye bath, which is what we will focus on, and the post dye bath step. So the dye bath is the crucial bath step where the color chemicals, dyes are also added to the solution and the fabric uptake of dyes happens. So one thing I want you to notice is that the salinity in the preparatory and the post dye bath steps is not significant. Whereas in the dye bath step, there is a significant salinity of the effluent that comes out, because in order to enable uptake of color by the fabric, the background concentration or the background salt concentration has to be adjusted. Okay? So a range of salinity is mentioned here with the expectation, with the fact that the amount of salt used is a function of the shade of color that we want to achieve in the fabric. So if you want a darker shade, then we would have to go to a more saline solution to enable higher uptake of color by the fabric. So we'll look at this in a little more detail going forward. So while it is sometimes preferable to collect these effluents separately and treat them, from a practical industrial standpoint, what is often done is to collect all these effluents together as an overall effluent, which comes out at an intermediate salinity between the other baths and the dye bath. And this overall effluent is either treated in the specific dyeing unit itself, or it is also sent sometimes to a common effluent treatment plant for treatment along with the effluents from other dyeing plants. Right? So the impact of the salinity of the dye bath on dye uptake. So this is something that has been studied in the past. So this is results from literature. I think Madan has published this data from 1970s, where they've looked at the dye uptake by the fabric as a function of the dye bath salinity or the dye bath normality on the x-axis. So you can see that the dye uptake increases as the concentration in the dye bath increases. And in this particular study, what's interesting is that they've also considered the impact of the solution chemistry. So as a function of the particular salt that is used in the dye bath, how much dye uptake happens. This has also been studied. So what you can see is that there is a dependence on the chemistry as a function of the salt. The amount of dye uptake does change significantly. Right. So the perspective from which we want to look at it now is to look at the energy consumption. So if you want to think about the energy consumption for desalination, we can think about it from first principles thermodynamics, and the least energy required is going to be independent of the actual technology used, and it is just a function of the incoming and outgoing streams. And if we apply the first and second laws of thermodynamics, then we can get that the least energy rate is going to be a function of the Gibbs free energy of the product stream, the brine stream, and the incoming saline stream, the feed stream. Right. So data is available, calculations have been done for the least energy for a simple desalination application as a function of recovery ratio. The data is presented here. You can see that as you try to recover a larger percentage of the incoming water as a product, the energy requirement increases. The energy is also higher for a saltier stream, and the energy is slightly lower if the product doesn't have to be ultra pure. So if the product is 0 grams per kilogram, then the energy is slightly higher. So a good number to keep in mind is like for seawater desalination, at around 50% recovery, the specific energy consumption is around 1 kilowatt hour per meter cube. This is the least energy input requirement. The actual energy requirement is around 2 to 3 times this number to account for irreversibilities in the process. Right. So the actual seawater desalination consumes around 3 to 4 kilowatt hours per meter cube, including pre-treatment, etc. So in the context of textile dyeing, we can again look at this least energy requirement and express this as a function of the solution chemistry. So here I basically expressed this expression in the form of the activities of the water and salt species. So here I goes through every solute species in the solution. Right? And the activity in this study has been determined using the Pitzer model for electrolyte solutions and using these two databases, the PyEQL or the Freak database. So what I've done is to reproduce the data on dye uptake versus dye bath salinity, but this time looking at the specific energy consumption using the formula that was presented on the previous slide. So what you can see is that the specific energy required for the desalination as a function of dye uptake is also going to be a function of the specific ion or the specific salt that is used in the dye bath. So here the ammonium sulfate and the ammonium chloride consume significantly lower energy in the desalination step for achieving the same amount of dye uptake. So this is based on just data presented on dye uptake versus salt, and I've just done the calculation for the energy required for the desalination. So broadly speaking, what we want to do is in an industrial zero liquid discharge kind of framework, where there's a small amount of makeup water that is taken up from a natural resource, but ideally most of the water is recycled within the industry through desalination. We want to change or choose the chemicals added in the processing step to affect or reduce the specific energy consumption in the desalination and water treatment steps. Right? So in the context of textile dyeing, even though a few different salts are mentioned in this slide, what I noticed is that industries usually use one of two salts or a combination of sodium sulfate and sodium chloride. So our study going forward is going to focus on sulfate and chloride as the anions in the solution. And the proposal is to eliminate chloride anions in solution in favor of sulfate anions to reduce the energy consumption for the brine recycling technologies. So the conventional brine recycling, as I mentioned, involves reverse osmosis plus multi-effect distillation followed by nanofiltration for polishing. What we have proposed is to, once you eliminate the chlorides in favor of sulfates, then in the place of reverse osmosis, you can actually use nanofiltration membranes for desalination. And also for the polishing step, we can use membranes with larger pores, such as ultrafiltration membranes. The reason for this is that the anions are now much larger. So the hydrated sulfate anion in water is much larger than the hydrated chloride anion. And also the sulfate being doubly charged, the rejection of sulfate is higher, even with membranes with larger pores. So we look at some of the advantages associated with this. So first, from a thermodynamic perspective, eliminating chloride, basically you can see that if I compare sodium chloride versus sodium sulfate, at the same salinity, the osmotic pressure associated with my sodium sulfate solution is significantly lower. What this means is that I need to apply a lower pressure to achieve the desalination. The pressure applied has to be greater than the osmotic pressure of the solution. So for the sodium sulfate, we need a lower pressure. Right? So that's from a purely theoretical or analytical perspective, the advantage of having sulfate as the anion. In addition, the practical advantage is what I mentioned in the previous slide, which is that if you use a solution which has only sodium sulfate or sulfate as the anion without any chloride, you can actually use nanofiltration, which is not usually a desalination technology, to effectively perform desalination. So here I've shown lab data for desalination of a sodium sulfate solution, all the way up to 110 gram per kilogram salinity, while still this is performed at applied pressure less than 60 bar and while achieving rejection of more than 96%. So in the industrial context, the product with 4% of the solution coming through in the product could still be reusable. Right? So in contrast, if I had used sodium chloride, the salinity up to which I could go is only around 60 gram per kilogram when the applied pressure is restricted to around 65 bar. That's the main advantage. So I'm able to go to around 2 times higher salinity while still operating with conventional pressure vessels and membranes. Right? So in the industrial setting, what is more important is actually the color repeatability. So here I briefly mentioned the theory behind how color is measured in the textile dyeing industry. So after you dye the fabric, what you want to do is to measure the color of the fabric. So this is done using this L star, A star, B star or LCH color space. So in this color space, the color of the fabric is identified as a specific point. So this is like cylindrical polar coordinate space. The the A and B axis denote the redness and greenness of the fabric, and the L axis denotes the lightness or darkness of the fabric. So color differences in this space, in this color space, are basically measured as a weighted distance in this space, where the weighting factors are chosen to account for human sight. So the weighting factors are chosen such that because our eyes are more perceptive in certain ranges of color, so to account for that, a particular weighting is chosen. So if this color difference delta ECMC is less than 1, it is often considered that the color is sufficiently good reproduction has happened, and from an industrial perspective. So here I'm showing the actual data of color reproducibility study, where we've used the brine solution and compared with the dyeing with a pure salt solution. So the closer this point is to the origin, the closer the color is to the pure salt solution. And so the point is within this circle, then it is sufficiently good reproducibility. That's the kind of picture that we will use for assessing the reproducibility in this study. So what we have done in this study is actually to go ahead and use both sodium chloride and sodium sulfate at different solution concentrations in the industry with three different dyes, and measure each of these axes, the color in each of these axes. So this is just plotted. So what I'm trying to highlight here is that clearly there is a difference in terms of the darkness of the shade achieved at the same electrolyte normality with sodium sulfate versus sodium chloride. But there is also some small differences in the green-red axis as well as the blue-yellow axis. But overall, the big picture idea in this slide is that using this data, I can choose the concentration of the sodium chloride to achieve a very close match with the color produced with the sodium sulfate. And once I choose these concentrations, I can compare the energy consumption. So on this side, I basically compared the energy consumption, the specific work, versus the existing sodium chloride concentration. So the sodium chloride concentration existing is 40 gram per liter. The sodium sulfate concentration required is around 30 gram per liter only, or from this graph, right? And correspondingly, the specific energy is also reduced. And on average, the reduction is around 35 to 50% in terms of least energy for desalination. Okay. So this is just from a theoretical perspective. What we've done as a next step is to actually sit in the industry and perform some cycles of operation with small batches of dyeing, where we've taken fabric of this size, dyed it, taken the effluent, treated it for color, and then performed nanofiltration as the desalination step, recovered the product and the brine, and recycled it to the next reuse of dye. So this is data across multiple recycling cycles with various colors of fabric. So what you can see is up to around 3 cycles, you can get good reusability with the color difference being less than 1. Whereas beyond that, the reusability, the color difference starts deviating due to the buildup of contaminants in the solution. Right. So in this regard, we have to now look for good polishing steps where the effluent, the brine can be actually treated so that the color reproduction is improved. So what we had tried here, so in the literature, we see a lot of data or reports on novel membranes, novel nanofiltration membranes and ultrafiltration membranes for dye and salt fractionation. So what we are doing here is not dye and salt fractionation. It is instead removing the treated dye molecules that are left out after the primary secondary treatment that build up in the solution after desalination. We want to remove all those molecules from the salt. So what we want is a pure salt solution for recycling in the dye bath. So with our with a simple commercial ultrafiltration membrane, it was possible to treat this water and reduce the color difference. So the color difference, as you can see, with this bright blue color was reduced by 50%, and this olive color is reduced by around 90%. So this is promising in terms of polishing. So that is one of the aspects that I wanted to highlight. The other aspect was tuned treatment for the industry. So as I mentioned, in the dyeing industry, the dye bath is where they add salt, and the amount of salt that is added in the dye bath is a function of the fabric color. So if you want to achieve a very dark shade of fabric, then a much higher concentration is used, whereas for a light shade of fabric, a much lower concentration of salt is used. Right. So from a treatment perspective also, it makes sense to produce brines at different salinity levels for reuse rather than going for full desalination. Okay, so we want to perform partial desalination and reuse the solutions at different concentrations rather than perform full desalination. Right. So in this regard, I have highlighted some technologies that can be used towards this. So normally reverse osmosis usually will perform full desalination because the membrane allows only pure water to pass through. Whereas electrochemical process, the electrodialysis process is a good candidate for this because we can adjust the voltage applied or the flow rate of the solution through this stack to control how much of the ions are removed. So in this case, we are removing the ions rather than the water. So by controlling how much of the ions are removed, the output need not be a very pure stream. So we can get partially desalinated stream as well as a slightly concentrated stream out of this technology. Right? Thermal distillation also usually produces only a pure stream. So we focused on electrodialysis for this partial desalination application. So what we have done is to collect the RO brine from the industry, which comes in at around 38 gram per kilogram salinity. And at the lab scale, we have passed it through the electrodialysis system to split it into 15 gram per kilogram solution dilute and a very concentrated 86 gram per kilogram concentrate. And both of these have been sent back to the industry for reusability studies. This will be reused in the darker shades and this is reused in the lighter shades. So while the energy consumption of this is much reduced compared to the thermal distillation process, which is the alternative technology, in terms of color reproduction, I think there is still work to be done because you can see that the solutions are not extremely clear looking, and so they have an impact on the color of the fabric. So with that, I'll quickly highlight some of the takeaways from this specific study. So I think there is scope for tuning the effluent chemistry towards reducing energy use and overall cost in the industrial context, mainly because unlike natural water streams, the choice of salts or choice of chemicals used in the dyeing or the other chemical industries is up to the industries, right? So that is one point. And the other point is that in terms of treatment, I think there is scope for tunable or custom solutions to recover multiple recyclable products rather than just use like normal RO like as a hammer. However, there are of course challenges. The first challenge is that process level changes are quite intrusive. So we need significant buy-in from the industry to implement a situation where the chemicals they actually use in the process are changed to reduce the energy in the downstream desalination. The other opportunity is to look for good polishing steps to further improve this reusability of the salty brines that are produced. And one more challenge is that the electrodialysis technology itself is not as widely commercially available as RO. So with that, I'll also like to thank some of the funding agencies. So the Ministry of Science and Technology, Department of Science and Technology at Government of India funded this work. And initial funding was also given by the Tata Center at MIT. So with that, I'll conclude my presentation. Thank you so much once again.
Thank you, Jay. Thank you for detailed presentation regarding the desalination technologies of the case study. And in the interest of